One of the things that I really struggle with sometimes with these formulas is, if the growth is continuous, you really can't use this formula, but a lot of books they do. Um, this formula, they say that this is the exponential growth or decay, and it makes sense to me, but I'll show you where I have problems sometimes. If this is my final amount, okay, so I always do it this way. So let's say, now we'll go through this. This is the final amount that you have. Turn my marker on here. This is the final amount you have. If the initial amount is this, and then you do 1 plus the rate if it's an exponential growth, and 1 minus the rate if it's an exponential decay, and then to the t power. So it's a fairly simple formula. For example, if you had a population of a city, so let's say I have a population of a city that is, let's say, 5,000 people, pretty small city. And it's increasing at a rate of, let's say, 5% for, let's say, 10 years. How many people would be in that city after 10 years? Well, we would just use this. This is a pretty straightforward formula. The initial amount, well, the population right now is 5,000, so that's my initial amount. So I would just go 5,000. And then 1 plus R, because the population is increasing. I said the population is increasing by 5%, so that's 0.05 to 10 years. And that would be 10 years here. Okay, so now I just plug this into my calculator, and I have just a real cheap old calculator here. I'm not sure if it's going to work here. I'm going to go 1 plus 0.0, oops, 1 plus 0.05 raised to the 10th power, and then times, what is that, 5,000, because that's my original amount, times 5,000. Okay, so my population after 10 years would be 8,144 people. Now, why is this important? Well, if you have a city and you have to build schools, and you have to, fire departments and police departments and stuff like that, you want to kind of plan things out. So if you know that there's going to be an extra 3,000 people, you're probably going to have to expand the school. You're probably going to have to, get more police department, the fire department's probably going to have to expand and stuff like that. Now, let's say we did the same problem, but we said that the city is decreasing. It's going down and it's losing people. Okay, so then I would do the exact same problem. I would go 5,000 and then 1 minus R. So that's going to be 1 minus 0.05. And that's to the 10 years. Now, if you look at this, if you add this together, you end up with 1.05, right? That's my R value. And if you subtract this, you end up with 0.95. That's my R value. And if the R value is greater than 1.05 is greater than 1, you know that this is exponential growth. If it's less than 1, if this value inside here is less than 1, you know it's going to go down. So I see that I've got 5,000 times 0.95 raised to the 10th power. I know that my answer is going to be less than 5,000 because this is the initial amount of the population. My R value is less than 1. I know it's going down. I don't even have to, you can just look at a problem and tell if it's exponential growth or exponential decay just by looking at the R value. And the R value is the value, raised to the power. So I'm going to do this problem. So I've got 0.95 raised to the 10th power, and that is multiplied by 5,000. And my population would be 2,993 people. So that is exponential growth and exponential decay. You should be able to tell right away if something is exponential growth or exponential decay just by looking at the equation. So let's take a look at some examples you'll be looking at tonight. It says Clara invests $5,000 into an account that pays 6.25% interest per year. After how many years will her investment be worth $10,000? Okay, so now we have to start solving these equations. So we have to use the information that we learned last week. So the first thing I'm going to do is I'm going to set up my equation. So my original amount is 5,000. And then this is going to be 1 plus, because the account pays interest per year, so 0.0625 to the t power. I don't know what t is. That's what I'm looking for, because it says that after how many years, so I'm looking for t, will her investment be worth 10,000? So that means that equals 10,000. Oh, now I have an exponential equation that I have to solve. And I'm going to solve it exactly the same way as we solved it last week. First thing I'm going to do, I'm looking at this and it's like, okay, I'm going to divide both sides by 5,000. So I end up with 2 is equal to, I'm just going to add this together, so that's going to be 1.0625 to the t power. Oh, now it looks really a lot like last week. So I'm going to rewrite this as the log base 1.0625 to 2 is equal to t. Now my calculator does not have that. I'm going to have to write this down. I'm going to go to Desmos, because Desmos has a great calculator. All right, so I'm going to go log of 1.0625 of 2. Okay, and that's going to be my t. Now I will tell you, I can kind of estimate what the answer is going to be, because I learned way back when I was taking a class in economics. It said, one of my teachers said that if you have an interest rate of 7% for 7 years, your money is going to double. Well, this is less than 7%, and I'm trying to double it. So I'm going to say that it's going to be a little bit more than 7 years. It's going to take a little bit more than 7 years to double the money here. So my estimate here, if I'm doing an estimate, I'm going to estimate it about 8 or 9 years that it's going to take to double. Okay, so I'm going to jump into Desmos. Desmos has the awesome log function where you can just plug in. Okay, so now I've got, oops, I have some extra stuff in here. So I'm just going to type in my log. My base is, what did I say, 1.0625 and 2. Ooh, way more than I thought it was going to be. 11.4. So it's going to take 11.4 years for the money to double. Okay. Kind of cool. You got to be able to set the problem up and then use the skills from last week to solve the problem. All right, let's try another one. In 1981, the Australian humpback whale population was 350, and increase at a rate of 14% each year since then. Write a function to model the population growth. Predict when the population will reach 20,000. Okay. So now this is 1981. So when I write my equation, I have to assume that my equation is from 1981. It's not from 2021. Okay. Because the population of the whales was 350 in 1981. Okay, so 350, 14%, so that's going to be 1 plus 0.14 to the t power. And I want to find out when this is going to reach 20,000. Okay, so I'm just going to put 20,000 here. I'm going to solve for t. Okay, so again, I've set up my equation. I'm going to divide through by 350 here. So 2,000 divided by 35, 57.14 is equal to 1.14 to the t power. So now I'm going to rewrite this as a logarithm. So the log base 1.14 of 57.14 is equal to t. And I should be able to solve this problem. Again, I have to write it down because I'm old and I forget when I jumped over to my Desmos. So log 1.14, 57.14. All right, so I'm going to jump into Desmos, get rid of this. So log base 1.14, and that's to 57.14. 57.4 and I come up with 30.87 years. So about 30 years it's going to take for that population. So I'm going to go 30 years. So if I add that on to 1981, what is that going to be? 2010? Is that 2010? Would that be 30 years? 2011 would be 30 years. So we can take a formula and solve for the time. Now, I will tell you that if they ever ask you to solve for the R value and they give you the time, you can still do that using logarithms and exponents. You should be able to set up any equation and be able to solve, okay? A city population with an initial population of 15,500 has been dropping 3% a year. Write an exponential function and graph the function. Well, we don't want to graph. Predict when the population will drop below 8,000. Again, I'm just going to set this equation up. I'm not going to solve this one, but my initial population was 15,500. It's dropping, so it's 1 minus 0.03, so what is that, 0.97 to the t. And I want to predict when the population will be 8,000. So there's my equation set up. Now, using your skills, you should be able to solve that. Now, why did I say I didn't like this equation sometimes? Well, this is a population problem, okay? And population problems, usually the population, usually we use what is called continuous compounding, okay? And you'll see tonight on a lot of your homework, it's going to be the same. It's going to be continuous compounding. The formula is very similar, okay? So we have A is equal to, in our problem, we have the original amount, right? I don't know what they called it. We'll go original amount and then 1 plus R to the t power. Well, if you have compounding continuous, we use what is called the PERT formula. And we already talked about this one. So this, if I was going to do this problem using the PERT formula, my original population was 15,000. I forgot one, E, and then R to the T. So I'm going to have 0.03 to the T power. And that is, I'll solve this both ways. And I'm trying to solve that till it gets to 8,000. Okay, so I'm going to solve this one, and then I'm going to solve this one. They're going to be fairly close. But this one is used more often than this one up here. But you should know both. And when you look at this problem, I don't think I can do this problem this way because it's dropping. I think I have to put negative in front of there because it's a negative. It's going down for that. Okay. So I'm not 100% sure you can do decreasing with PERT formula because PERT formula is always increasing because the E value, because you look at that. So I'm going to say you can't use that on this one, but I'll show you which ones you can. But it's basically the same formula. All right. So let's take a look at a problem like this. It says the number of bacteria in a culture is modeled by the function n of t is equal to 600 e to the 0.5 t, where t is measured in hours. What is the initial number of bacteria? Oh, so this is the PERT formula, P-E-R-T. This is the initial amount. So this is a fairly easy problem. Initial 600, done. Try another one. It says a fox population in a certain region has a relative growth rate of 7% per year. It is estimated that the population in 1997 was 18,000. Find a function that models the population t years after 1997. Now, I'm looking at the answers and it's like, okay, they're using the PERT formula. So the original, 18,000 times e to the RT, well, 7%, that's 0.07 t. That's it. I'm done. I don't have to, they just said, come up with a function. Okay, so let's see here. Letter E would be my answer. Now this formula, if I'm going to use this formula, remember, it starts in 1997, okay, because that's when the initial population is. So if they said, what is the population in the year 2000? Okay, your t-value would be 3 then, because 1997 is year 1 or year 0, and then we're just adding 3 years on. Okay, so you have to understand when you're writing these equations, it is from the time that they tell you. Okay. In this problem, it says the number of bacteria in the culture is modeled by the function 100e to the 0.35t, where t is measured in hours. What is the initial number of bacteria? Fairly easy. That's my initial. If they ask me, well, what's the rate of increase? 0.35. All right, so, but they didn't ask me that, so just letter E.